Alright, so let's get started. So I'm SSHing into my department machine. So let's get into our folder. Okay. So for people who haven't even started with XV6 yet, I'm going to start from getting the tar file, untarring it, and then setting it up. So pay attention if you haven't got that stuff working yet. So we have said that the source file for XV6 will be in this directory. So we just copy that file over. Note that in order to do this step, we actually need to be logged into the CSL network. So that is an AFS share, a file which is present only inside the network. You can't do this on your home computer. So make sure that you are logged into the network when you do this. So once you have the tar file, you can go ahead and untar it. So you should learn commands while you're at this project. So tar is a very useful command. And what we're doing is we're just untarring this particular file and getting all its contents. So X means extract and Z means because it's a tar.gz file. V is verbose, which means it will tell you what it is extracting, and F is extracted from this file. All right. So we have our XV6 folder. We move to the XV6 folder. By the way, if at any point during the demo, if you get confused or if you want me to repeat any action, just raise your hand and we'll go do it again. All right. So here we have the XV6 code, and if you remember the README that we gave you, the way to run this is you do make QEMU, which compiles the whole kernel, and then gets you a new shell in which your new kernel is now running. So this is QEMU, which is like a virtual machine emulator, and what you're seeing in there is your new kernel, brand new, compiled and running, right? So let's check something in our new kernel. Let's do an ls. So if you do an ls, it will tell you what all files you have in your current directory. So it shows there's like the readme, the cat, the echo, and all of those stuff. It's an educational kernel, so there isn't a lot of it in there. But the kernel is so small that you could read the whole of the kernel and understand most of it. So that's sort of the reason why we picked XV6 and not the Linux kernel to do these sort of like experiments in. Alright, so that's how you get XV6 up and running. And anytime you make any change to XV6, you will follow the exact same step. So you'll quit this, you'll do make QEMU, and then the emulator will come back up with your newly compiled kernel. Make sense? Okay, alright. So given that that's done, let's go ahead and look at what we need to do. So I just quit that particular emulation, and we are back in our CSL machine. So for project P1, you will be adding a new system call into XV6. And anytime you're learning anything about a kernel, if you can add a new system call in there, that means you've mastered a big part of it. So you'll know all the architecture of the kernel, where things are, and so on and so forth, right? So if you remember the sort of like README file that we gave, we said that one way to do this would be to look at how an existing system call is implemented in the kernel. So that's what we're going to do. So what we're going to do is we're going to use something called grep. So this is sort of like find in Notepad, but way more powerful. So what we're going to do is we are going to search for get PID in all of the files that we have here. So these are all just like flags to grep. I'm not sure if it's capital or smaller. We'll find out. But basically what we're saying is with the capital I, we're saying don't search in binary files because we did a make. All of our the kernel is compiled. We don't want to look into the kernel binary and see that get PID is there. That doesn't do us much help. The -i says ignore the case, and then R says recursive. So I forget if it's capital or small. Let's try small. All right, thank you. So we get a bunch of files from grep which tell us like where we can find get PID. So you can see there's a bunch of stuff in kernel. So these are all the things as to how get PID is implemented inside the kernel. There's also a user space component because system calls that are only in the kernel are not very useful. You need a user space component so that programs that you're writing can access that system call. And there's also an include file which sort of is the interface between the two, wherein you do something in your user space and you tell the kernel, and then the kernel then knows where to find it. All right. So what we're going to do is we're going to send this to some file, and then we're going to take a look at each file. I'm going to explain what's in there. All right. So okay. So you can see that we have like 8 files that we sort of need to look at. Let's start by doing this from user space. Everybody can still see, right? Hopefully, yes. All right. So let's start with user user.h. So this is the file in which we are defining all of the system calls that we are going to call in our programs. Now, if you remember in class, we said that when we are actually calling a system call, we are doing a trap to the kernel, right? So, but in our program code, we don't want traps and assembly code to be part of our program. So what we do is we write wrappers over that sort of assembly code, and we use them as functions. So what you are seeing here is the functions that we have in user space to sort of like wrap around calling and trapping into the kernel. Okay, and we will see in a moment how this gets translated into an actual trap call. So in this space, what we're doing is we're just like defining all the different system calls that we're going to call, and these are all just C functions at this point. We're just saying that there's a function called getPID which does not take any arguments. So in C, when you define a function, it makes it so that when you're compiling any file, the compiler will check that you have the same argument. For example, if getPID required an integer argument, you cannot call getPID without that argument. So this gives us a way to check at compile time whether programs are calling these wrappers correctly. Make sense so far? Okay, let's go get to the next part of it. So obviously when you are adding a new system call, you would want a wrapper so that you can access it in your files. So the first part you would change is you would have another call in here which says add num or whatever it is that you want to call your system call. All right? Yes?
This file basically defines all the system calls that are open, like available to the user.
They define the wrappers that are available to the users. So you can have a system call and you cannot have this file. What that would mean is you would have to do the assembly yourself in the program to call that system call. That's basically what it means. Okay. Okay, so we have taken a look at the first file, which is this part. So that's this part is done. So the user test.c is just a file wherein you're exercising your system call. So what we are seeing here is that like there's a program and it's calling this wrapper that we have for the system call, and then the return ID, the ID of the current process is then supplied in the return value and it's assigned to a variable. So this is all very common and normal stuff. So this is just how we would use a system call. The point here to note is that when you're adding your new system call, you will have to write a file such as this in user to make sure that you're exercising your system call. You have to make sure that it works, that it returns the value that you expect it to, and so on and so forth. So this would be, you can think of it as a unit test for people who have done that sort of stuff for the system call. All right, makes sense, hopefully. So we've taken a look at this. Now we're going to get into sort of the meat of the thing. Okay. So this is assembly file, and what it's doing is this is actually implementing the real system call stuff. So what it's doing is every time you call a system call, this is a macro by the way, but we will see how it actually gets transformed. But the macro is saying every time you get some name, define some variable called global name, and then in that what you're going to do is you're going to move something, a number, onto this register EAX, and then you're going to interrupt the kernel, and you're going to pass along a number which says it's a system call, and then you're going to return from that. So it's just 3 instructions. The first instruction, line 7, is basically saying what system call we are invoking at this point. The EAX register is being used for that purpose, and then we are interrupting the kernel, and we're saying remember that the int is a trap, which means we use it for many things apart from system calls, right? So here we are saying that, dear kernel, I'm interrupting you, but the reason I'm interrupting you is because this is a system call. Does it make sense so far? It'll get deeper and deeper, so it's better that you, if you don't understand the stuff, you ask me now. Make sense? Okay. So here we have actually used the macro that we have defined above, and what it does is it just says that there are different system calls with all these names. So if you look at it, each of these macros will be expanded by the preprocessor. And for example, for getPID, what will happen is uh, this is the only part of it where the name is used, right? The other part is all generic. So what will happen is it will say something like movl sys underscore, this is the concatenation operator, and it will say the name. So this will eventually end up as movl sys underscore getPID into EAX. Okay, and that's how we know that they're doing a system call, and the system call is for getPID. So let me see. There is one place where you can see where it is. Ah, yes, systcall.h. So, in case you're getting a little confused, um, so do you see this? So do you see sys underscore get PID is defined as 18? So the number that we are pushing into the EX register here is actually just this number. We're just taking the name, we're prepending sys to it so that we get this variable, and then we're pushing that variable into EAX. So the system call for getPID in sort of like raw hardware will look like this. You push 18 into the EX register, and then you interrupt the system, the kernel with t underscore syscall, which is actually 64. So push 18 into EAX, push 64. I mean push interrupt using the number 64, and then return. So that is all the system call actually translates to.
What happens if there are any arguments in those?
So the way it works in XV6 is because we are using wrappers for all the system calls, the arguments will be on the user stack, right? So you have made the call, and then like on the stack you can find argument one after the other. So XV6 knows that those arguments will be there, and will just pull them from that location. Make sense? Okay. So hopefully you are with me so far, because we are now going to get into the kernel, which will be even more hairier than this stuff. All right. So before we get into the kernel, let me summarize once more. So we have the user space programs. Uses.s is where the actual system call, the assembly thing, is defined. User.h is where we're defining the wrappers so that we can use the system call in our program. And user.test.c are just like files where you exercise the system call. Okay with me so far? All right, let's go look. Let's go look at what the kernel is doing. So okay, so this is the file in where all the functions are defined within the kernel, right? So think about what a system call is doing. So you have a wrapper in user space. The wrapper will will have some arguments. When we call the wrapper, we are then we are then trapping into the kernel, right? Upon trapping into the kernel, we'll be going to a trap handler, which will then execute some function in the kernel because of this system call. So this is all the functions that get executed inside the kernel when you have the system call trap. So remember, I mean, if you're getting confused as to why there are two functions, remember that one is a wrapper in user space and one is the actual implementation inside the kernel. Okay. All right. So this is where you're defining all of the different system call handlers inside the kernel. So let's look at something more fun. So this is the file sysproc.c, wherein we're actually defining all of the Here we go. So this is all the definition getPID does actually. So proc is the current process that's running in the kernel. So it just looks at proc, and there's already a field in that structure which I showed you in class if you remember. And then it looks at proc and it says what's the current PID. It just returns this value. This is all your getPID is doing, and the implementation of your add_num system call will be equivalent to this. It will be very simple. It will be 1 or 2 lines max. So the goal of this project is not to get you to implement some complex system call, but only to make you familiar with the structure of the system calls in the system. Okay? So this is, yes? Question? Okay. So remember that this is the core of the system call. All the rest of it is just like plumbing so that you can get from user space to this particular value. Okay? So that's one part of it. Then we have syscall.c. Okay. So do you see this particular table? So this is what we call a list of function pointers. How many people know what function pointers are in C? Fair number. Okay, pretty good. For those who don't, a function pointer is basically you can pass along the name of a function as an argument to another function. An argument anywhere actually. So you basically can say things like x is this function, and then you pass on x to somewhere else, and they will execute x using that function pointer. So here what we are doing is we are defining all these different functions, and then we are saying um, if you index into the table using this particular number, this is what you get. So if you remember, we had a sys_getPID previously in include the file. What this is saying is, if you get a system call with that particular number, this is the function that you should invoke. Makes sense, right? So this is our trap handling that we had talked about in class. We get the trap, we look at this table, we look at the number, and then we execute the function that's there. If you're wondering where the code is for all of that, that's just below this table. So this is actually pretty funny in the sense that this is all the code there is to implement system calls. It's just generic code, and it's like 10 lines. So what is it doing? What it's doing is, first, it's getting the number of the system call from EAX. All right. Do you remember where we put this in? Let me see. So this part of the code is where we are taking the system call number and we're putting it into EAX. And here inside the kernel, deep inside the kernel, is where we are popping that value to get the number of the system call. Okay. So what we're doing is we get the number and then we do some basic error checking. So is the number greater than 0? Because we're indexing into an array, we don't want negative numbers or 0. Then we say, is the number lesser than the total number of system calls there are in the system? So if you only have 100 system calls and somebody calls in somehow 1000, you want to be able to identify that. Alright, and you don't want the function that you're executing to be null. So that's another thing that we are checking. So if all of that works out, if you are able to find that the number is legitimate and that the function that's defined for this number is also legitimate, what we do is we call that particular function. So to sort of like make this clearer for you, this would be one way of looking at it. So syscalls a num will get you a function, right? Because the table that we saw above is full of function pointers. So when you index into it using num, you end up with a particular function. And then this is just your normal function calling convention. Like just as you call syscall, for example, you just like call that particular function. Okay? This will actually sort of resolve into something like this actually. So sys_getPID. So this is what this will resolve into finally. So what we're doing then is we are calling this particular function and then we're putting the return value in EAX. So in xv6, the convention is that whenever you call a function, the return value will be stored in the EAX register. So that's what we're doing here. we are calling the function that's meant to be for the system call, and then we're putting the value in EAX. Make sense? Okay. So, sweet. All right. So that is basically all of the different files that you will need to understand what to do in the Linux kernel. So we looked at this. This is just the signature in the kernel. This is where it's actually defined, and this is where actually you're calling it inside the function. Let's just get rid of this. So that's it. So you have 7 files, I guess, and 3 of them in the kernel, 3 of them in user space. When you change all of those things, voila, you have a new system call in xv6. Does it make sense? So if you have questions about this, you should ask me now, because what I'm going to do next is I'm going to go from user space to the kernel. I'm going to show you what happens, how we set up the trap handler and stuff like that. So that'll get even more hairy. So this is the motive for this class. It'll always get more complicated. So makes sense so far? Yes? So if you look at, so I'm not going to tell you everything. So if you look at the get PID call, like if you do grep just similar to this, you will find out how they actually handle argument calls. So let's give you an example. Okay, so we have all of these files. So do you see this? This is sort of how they handle arguments. So what this is saying is that get me the argument at number 0 and put it in n. That's what it's saying. So this is slightly different from how we would do functions in C. So there are mild differences here and there, but as you execute the code, you'll sort of understand it. So just look in sysproc.c. There will be a bunch of functions which are using arguments. It should be pretty simple to figure out. Okay. All right. So given that all of that makes sense to you, I'm going to close this. So one more thing is, how many people here have used C tags? Okay, heard of C tags? Okay, that's much better. So basically, what we were doing presently is we were grepping all over the place, right? We looked at where a function is, and then we saw what file it was, and then we went and looked up the function. So there's much easier ways to do this. So one of them is C tags. So what I'm going to do is I'm going to run C tags for you and then show you how it's done. All right, what do we want to look at? I want to look at stuff here. Okay. So what C tags will do for you is, let's say I want to look up where this function particularly is. So I'll give you keyboard shortcuts to do that. So watch the magic. So we are at the definition of that particular function, right? Then we looked at this function and then we want to go back, another key press, and then we are back again. So the key bindings will differ based on whether you're on Mac or on your Linux and so on and so forth. So I'll leave it to you to figure out that. But know that using C tags, you can navigate the code base much more effectively than by grepping. Okay. And in fact, the rest of the demo, while I'll be showing you what's going on, I'll be using C tags so that you can see how you can jump back and forth relatively fast. Okay. All right. So what is this file that we are looking at? So remember in class, I told you that the way protection works is when the system starts up, we will do a bunch of stuff. We will do trap handlers, and we will tell the hardware where the trap handlers are. And what this helps us is during a normal execution, it allows us to stop user programs from doing bad stuff. So now we are going to look at how we set up all of that stuff at the start of xv6. So all of this will help you understand how system calls are actually being implemented. But all the stuff that I'm going to show you now, you will not actually be needing for this project. So if you're very worried after looking at this demo and thinking like, oh my god, there's so much stuff, I don't understand any of it, you are in luck because you don't need it for this particular project, but you will eventually need it. So you need to go and look at it. Okay? Alright, so main C is sort of the bootstrap code for xv6. So in this particular code base, it first starts out by printing starting xv6, and it does a bunch of setup stuff. And one of the setup stuff that we are interested in is trap vectors that we're seeing here. So we want to understand how trap vectors are set up, because this is what will be invoked when you're doing any system calls, because all system calls are traps. Okay, so using the magic of ctags, we go here, and then what we are seeing here is that there's a macro called setGate. And what this setGate is doing is it's doing a bunch of complicated stuff, but thankfully we can identify our favorite t underscore syscall word and we can latch on to that. So when you're reading code, by the way, there will be a ton of detail. You don't have to understand all of the detail to understand how everything works. Make sure you focus on stuff that you're currently interested in. So we are currently interested in how syscalls work in XV6. So we're going to ignore this first line, which is basically doing something for memory management. This is setting up the segmentation, the K code, and then doing some stuff. We're just going to ignore that line, and we're going to focus on what's happening at the next part of the line. Okay, so what's happening here is that we are setting up the trap handler table for XV6. So we're basically saying there's a table which has all of the system calls, we have some other factors in it, then we're saying that is going to be associated with this vectors of system calls. Okay, so this is just the in-memory table of the trap handler. And we can go look at what the vectors are, because they helpfully say that it is present in vectors.s. So let's go look at vectors.s. Okay, so this is the file which implements all of the vectors required for your traps. So if you are the kind of people who get really excited looking at like assembly language and like this is the real deal, this will be very happy for you, because you can look at the whole thing in assembly if you want. So what we are seeing here is that we have a number of vectors defined, and each vector is sort of translates to a trap. And when you get the trap, you look at the vector and then you go see what it's doing. In particular, we are interested in vector 64 because I happen to know that that's what you gets called when you do a system call. The number for a system call in XV6 is 64. So whenever you do a system call trap, this is where it ends up. It will push 64 onto the stack, and then it jumps to this particular function. If you look at it, all of this code is basically the same thing. It all calls into all traps. So XV6 is simple in the sense that all of your traps are going to one place, and then in that place we will handle different things in different ways. With me so far? Okay. So let's look at what this is doing. So all traps is a function wherein we are building the trap frames, we are setting up the data, and then we are calling a function called trap. Okay. So if you remember in class, yes. When this particular system call happens? Right. So let's go back a little and we can see that. So do you see this? So here we are setting up the table for the trap handlers. We are saying that when you have these particular system calls, these are the vectors that you should look at. Okay, and this function just below that is where you're telling the hardware about this table, right? If you remember in class, we set up the trap handler table, and then we will tell the hardware this is where it is. So when you get the trap, the hardware knows because of this instruction. The hardware knows to look at this particular vector, and then based on the number in the interrupt or the trap, it will go look up a particular thing in that vector. Okay, makes sense. Good question. Let's go back. So back to vectors, and then back to all traps. Okay, so we are back at all traps. So in class we said that when you do a trap, that is when you move from user space to kernel mode, right? So you have all of the variables in your user space, and you are now going to trap. Remember that when you come back from the trap, a different process may run in user space. It doesn't have to be the same process. What this means is whenever you're trapping, you have to save the user process state, because when you come back, it may not be there, and you want to be able to resume all the processes which were trapped and now got into the kernel. Okay? So this is what we're doing, and we are calling the frame or all the data that you require to trap and then return from trap successfully as the trap frame. And we are pushing a lot of the data that's usually in user space into the trap frame. We are pushing the values of all the registers, AS, FS, and so on and so forth. We are setting up all the data, and then we are actually doing the trap. This part, the lines 8 to 21, is essential because if you did not do this, you cannot resume a process when you return from trap. This is the part of the code which does that magic for you. Make sense? Okay. So finally, after saving all of the user's state, we are going to go ahead and we are going to trap. So let's look at what trap does. So we are back in the C file that we were before we went into that assembly language detour. We are back in user space, and you can see the first part of it is exactly what we're interested in. So what we're looking at is like if the number of the trap that we were pushing onto the code back when we said t underscore syscall, we check if it's that particular trap. We take a look if the process is killed or not, because all of this goes on in parallel with other stuff in the system, and your process may be killed at any point of time. So we check if the process is killed. If not, we actually have to do some work. So we look at the trap frame for the process. We set it to the process's trap frame, and then we actually do the system call. Once you're done with the system call, we again check if the process has been killed, and then we return. Okay. So this is the sort of crux of it, and this is the function that we already sort of looked at. So if you are with me so far, what you have seen is we set up a lot of stuff, the trap handlers. We went from the trap handlers to vectors. We went from vectors to all traps, and from all traps we jumped back into this trap file, and from there we call the system call code. So that's the whole chain as to what happens when you call a system call and how you actually end up in this code which does the system call for you. Does this make sense?